way down the ground, to say, or something's on the right, no,
We have here sort of Joe rectangle.
It's a pretty poor rectangle. It's got a little bit of jaggedy.
yeah, it's got jagging there and it's got stoning down there.
And even though you use rule, I'm sorry, it's not sufficient.
Yeah.
Yeah, I'm down, there's that blob where his area is falling out there.
Plato again, you never see the objects in that planets, you only misrepresent them. So, a rectangle. Yes.
Would you just repeat the original question?
Oh,
Oh, yes.
Can you tile a rectangle with
Wait,
non-contour
slow down.
squares?
And you tile,
Mhm.
A rectangle.
With non-congruent
Rectangle with
squares.
non-congruent squares.
So each two squares that you use have to be different.
yeah.
Yes, right. And that's.
So that's
crucial
seriously
to ask.
non-congruent.
Thanks.
Yeah.
Because especially the 8 to 10-year-olds, they say, I don't know, I'm sorry to say, I don't know what congruent means, especially non-congruent. So he does. No two are the same.
Tiles just mean covered.
Tiling means, yeah, go on, anything but covered.
There's no empty space, right?
No,
Well, if you just took a square, which is a rectangle, then you could have one square on top of
And
it.
when we did this in Waterloo, at that audience of 500, one of them was a plumber. He said, can I use grout? Of course you can. I mean, why not? Mathematics is freedom. It would probably be more interesting not to do that. It'd probably be more interesting to cover it. Go on with cover. You mean,
Are you suggesting that you could take the rectangle and get a very large square
and put it over.
and put it over the rectangle?
That'd be ridiculous, but sure.
Yes.
So we would have to say, yes, that is a legitimate tiling of the rectangle with one. Can one square be non-congruent? There's our philosophical question.
All the ones involved are non-congruent.
The other one's empty.
So,
Square of side length.
sorry, say it again?
So the square of side length 0.
Yeah,
Tatiana, got a question?
so she's waiting.
Do there have to be a finite number of squares?
Did you say that it had to be? Go on,
Well, I was thinking like, we could take it, we could divide it up into pieces.
Yeah.
Like I have a particular example that I'm thinking of that works well,
Oh,
but I'm not going to say what it is.
Okay.
But and I could tile it.
This is a co-op.
I could tile it with an infinite number of squares. But I'm not sure like what are, again, I guess I'm trying to figure out like, is that still a, because you could kind of like, if you can make them really small and infinitely small, you could probably just like shove them into the corners or something.
Angle, perhaps.
I believe I'm repeating the question, but I want to make sure that I understood the question and the answer. Our tiling, no two squares should be congruent.
That's right. No two should be congruent. We now have following lines of thought developed. Yes, you can do it with one big square because covering could mean overkill. Just drop one big square on top of it.
This is
So there's a solution.
the splat solution.
And that's a lower bound to the conjectures, one square. Saying, maybe there can be an infinite tiling in a way that you have in mind that aren't going to tell us. Could you just
But like, I don't know, I was kind of trying to think some sort of like greedy algorithm type idea. But you take out the biggest piece, and then you take out the next biggest piece, and then the next biggest piece that isn't congruent, and then fit more pieces
what does
in.
it look like when you're done?
There are a lot of pieces.
Quantitative answers trump qualitative.
I guess like I'm trying to like, I don't know, I feel like I don't like the splat solution. I like having none of them overlap, so I'm just trying to.
So probably that's a good aesthetic choice. No overlapping. And we haven't got a lot of pieces. Yes.
I don't know if that would, if you do it greedily, maybe the next piece will become the previous piece. You want
Then you
different.
break it up into smaller pieces.
The gold rectangle would work, right?
Yeah,
Chop one off, copy of it, you chop it and then the next square off. I can see that.
When you chop off the biggest,
Yeah, in Joe here, it's not good if that's gonna work.
Right.
Because you're gonna have one big piece on the right, but then you're gonna have one skinny one on the left. So you can square it with the little one, and you wanna have like maybe 5 in a row on the left there.
That's
And then you try to
we're all right.
By the way,
Oh,
another,
there's Joe.
And, yes,
I'm just changing the subject, just because,
Good.
in addition, well, go back to what you were talking about after this. Can you use induction?
no, can you?
What I'm suggesting is include induction.
I think it's a terrific idea. By the way, now stepping back from the problem and looking at running a masterful class, one has a lot of different intuitions, different points of view, different levels of sophistication in one's students. Our classes have to be small, 10 or 12 is a maximum for us because of this conversation. But even there, you're going to get a range where someone will have heard of induction and others won't know what's being talked about. So yes, what we would do in such a class is ask you to explain what induction is, maybe give an example, some of the first-hand pictures, and then see, well, can that apply here? By the way, if we did do induction, do we have the n equals 1 step?
I'm sorry?
If we did do this by induction, do we have the n equals 1 step?
No. If the original rectangle is not a square, you know.
Well, there's the plopping of a big square over.
Oh, wait, I'm sorry?
There's plopping a big square over it. It's not fitting inside, but it is covering it. Well, unless you don't like the covering. Unless you don't like that. Dropping a big square over the rectangle.
Wait, I must have missed something.
Okay.
Because I came a few minutes late, so I'm not going to mark it down.
My suggestion was, yes, you can tile this with non-congruent squares, namely 1. Just take a big square and put it on top of this rectangle, so the rectangle is buried under it.
Oh, there's over it.
Oh,
And it's not a perfect match.
and it's not a perfect.
Oh.
But I saw dissatisfaction on it in half the faces.
And yeah, I like the idea of induction. I think it can be done. Because you know why? Because we can, I was trying to think, induction on what? Induction on the number of squares you need. So if you have 1 square, there's a rectangle that you can't do it for 1 square. And I can think of a rectangle you can't do it for 2 squares. So probably you can do it by induction, and you can prove it if you can't do it for 2.
Fantastic. So here's the second idea that comes up. This is the way mathematics is done. As Rakotosh says in that great book, it is try both to prove and disprove at the same time. So maybe try to disprove that such a tile can be done
But I think he should
by
do it by
induction.
himself.
Yes.
I'd say if you're actually covering rather than tiling, then you can do it with 1 square. It simply seems like you can do it with 2 squares by just having a line somewhere in the rectangle, and then 1 square covers 1 piece of the rectangle, and another covers another piece. And I wouldn't argue, but you should be able to just sort of keep doing this, and certainly up to 4, it seems like.
Right.
And so it becomes an easier problem if you don't tile, but just cover.
Nice point.
It's not clear that that easier problem helps you get closer to, or maybe it's clear that it does not help you get closer to covering the rectangle. If you tile the rectangle, you cover instead of tile. And of course, the other thing, if you really get carried away, if you cover, well, why bother covers that don't overlap?
Sorry, why are you covering?
If you're going to cover them, there's no intrinsic reason why you have to restrict it to just non-overlapping squares. So you just take a square and cover the rectangle with that square, and then put a second square over that square.
Yes.
Keep going, and then you can do it for any angle. You can cover it.
What happens, this problem, it takes us all the semester to do 10 1-hour classes. And had we that time, we would follow out each of your leads, slow everything down, because we have an hour. We're going to make a jump cut and say, if this is all right with you, and say, look, let's make this covering an exact covering. The squares have to fit inside that.
this is, after all, your back patio, and you're going to have every bit of it tiled. You can't leave a water feature in the center.
And we have several lines of thought. 1, prove that it can be done somehow. 2, prove that it can't be done. from the prove that it can be done line of thought comes when maybe induction will help us there. It can't be tiled with one. A non-square rectangle can't be tiled with one. Good, there's the n equals 1 step. And Mark, you said you see a way it
For
can't be
every
done
n, I want him to find a way. That there exists a rectangle that you can't tile with exactly n difference.
two non-congruent
Yeah,
squares.
You cannot
So
tile
n
any
equals 1 and n
rectangle.
equals
Sorry, say what?
You cannot tile any rectangle with two non-congruent.
Why? If you were 8 and 10-year-olds, this would be an important question. What does tiling mean and what does non-congruent mean? I guess that's what's being focused on by that question. You have a big square.
You want to draw a big square?
Yeah. Is this a transparency? Yes. Wonderful. So you have,
Shall I do half of it covered with a square? I mean,
so you take the short side
I'm
and
going to
rotate
take
it.
the short side, swing it down, hits here.
And now you have one more square left, and you have to tuck it into what's left. So you tuck it into what's left. And it's going to have to be the short side, will be the side line. So you rotate that up. And,
So we put a square in here.
yep. And this is why you're saying it can't be done with two squares. So good, we're on the way to an inductive proof this can't be done. Can't be done with one, can't be done with two. Yes.
But that's not going to help us with the case of infinitely many squares.
What? Yes. We've got two problems now. One, we don't have the infinite case, and two, we haven't done our inductive proof. We can't be tiled with one, and can't be tiled with two, maybe we can be tiled with 19.
No, it can't be. If it can't be done with two, then it can't be done with three. Just take away the square, the first region that you covered, and you've got a rectangle.
Right.
And you've got two left. You can't do it with two. You've got a rectangle left.
But that's only if your first square eats up the whole shorter side.
Don't we always have a problem where whenever we're putting the last square in, then that shares a short side with something else?
Great. In other words, that's being made of two that can't be done. Come to one. Does that make sense?
Yeah, like if we're restricting ourselves to a finite number, when the problem is the last square. And so
The
that's whenever we
smallest,
have
the
last
interesting
square, we
is
have
the
short-
smallest square. It has to be inside, it cannot be on the border, it cannot be in the corner. So the
Why can't it be
smallest-
in the corner?
The smallest square cannot be in the corner because
Yes. This is doing mathematics. Great hypothesis. If there were a tiling with a finite number of squares, there would have to be a smallest number.
Yes.
The smallest can't be in a corner because
can you draw
I will
Yes.
draw a very small one in the corner,
Bigger one next to it.
and a bigger one
therefore, there has to be a
next
bigger
it.
one next to it. What do you mean by next to it?
Staring edge.
To the left or?
Actually, yes,
Right
like
there.
this.
And therefore?
And therefore the next will not fit in this.
Terrific. Were there a finite tiling, it would have to have a smallest square, and that smallest square can't be in the corner. Therefore,
Therefore, it has to be in the middle, and therefore there has to be at least four more squares.
good. So the potential inductive proof has hit a snag. It can't be done with one, it can't be done with two, it might be doable with five. Five is what you're suggesting.
Well, it's bound.
At least five. The smallest square somewhere floating around in the middle, and these four windmill sails around it of different
Is
sizes.
there anybody with spare Kleenex?
Here, I have a spare penis. This is magic. Squares are going to disappear before your very eyes.
Very good.
So why can't the smallest be on an edge?
Yeah,
Let's
right,
try
right
it.
on an edge instead
Yes,
of in the
put
corner.
the same. So both side corners, we need to put a bigger rectangle there. So two bigger rectangles to both side corners. So that would be again a piece of street.
So we get a corridor.
This is what our students attempted to call the corridor problem. Smallest square in corner or on an edge leads to the corridor problem, which either says we're now getting a proof that this can't be done, or we're getting this constraints on where the squares can be and what kind of squares. The smallest square would have to be not on an edge, not on a corner. Not on an edge, just.
If you're not on an edge and you're not in the corner, you're somewhere in the middle of the field.
Not tilted, I assume. Yes.
And further, your smallest square, it cannot land in the middle of the edge of its neighboring square. It must share a corner with each of its neighboring squares.
Why exactly?
It is for the exact same reason you can't put it on the side, because you would still end up with that same corner.
What a nice generalization.
Harder problem with squares.
So you're saying that means?
Well, if you put, you can take out 3 of the corners there,
Yeah.
the squares, but then you've got a harder left.
True. It's a big card. If you mean,
This is
oh, you
what
mean
we're saying.
in there, in there. Well, you can always move the square up.
Yeah, but then add another square.
Yeah, but then add another square. We're just chasing the card around.
Yeah.
We're moving it.
Chasing.
At this point, we're 20 minutes through. Let's think about mathematics should be done democratically. How many people say that it cannot be done? Go to find a number of times. 1, 2, 3.
Yeah, what others are
See, it can't be done.
I don't know, we didn't vote that it could be done.
You're right. How many people did you check for?
Yeah.
For every rectangle or for some rectangle?
Oh, yeah, it's very vague.
It certainly can't be done with a finite number of rectangles if the original rectangle is, finite number of squares if the original rectangle is square. It can be done with one.
If the original rectangle is
It's a
square.
square.
Oh. What if it's not, but just some sort of rectangle? A non-square rectangle?
Well, if the ratio of the sides is a golden ratio, then something interesting can happen.
Should we present what interesting could happen?
Yeah, where to follow up again? I mean, all mathematics deals with the infinite. Go back to your cycle. We say back to your cycle. Say something.
Well, as I was saying, is we always take away the largest square bit, then maybe then we take out the next largest square bit, then the next largest square bit, the next largest square bit. You're always, as long as you don't end up with a symmetric piece at the end, then you can always take out another largest square bit and have something left over.
Now think, analogically, historically, draw on your knowledge. What does that remind you of?
It's the Euclidean algorithm.
Oh, indeed, Euclidean algorithm. That's the beautiful proof of it. Just keep doing it. What else?
It's a golden rectangle.
Well,
There's a golden rectangle. You certainly can tile a golden rectangle with an infinite number of squares. If we have an internet connection, I can show you a picture.
So in other words, there might be some technical problems here, but we might be able to overcome them. You're saying if the proportions of the original rectangle were 1 by 3, 1.61, on the square root, then you take out the largest possible, i.e. the largest possible square, or square with the side of 1. In what's remaining, you repeat the process, repeat the process, repeat the process. So we're going down and down and down in size. How's the Fibonacci series go? Recited? Start again. What'd you say? 1, 1. But that's a problem. We now have two congruent squares. Is this going to be a problem? You're looking unhappy about that. Well, I'm unhappy about it. Your face expresses that unhappiness.
Why are you unhappy?
Well, because the golden mean is the limit of the ratio of basic entries in Fibonacci sequence approaches. And Fibonacci sequence begins 1, 1, 2, 3, 5, etc. And 1, 1 suggests that we're going to have 2 congruent squares. And 1.
Well, they'll be infinitely
There they
small.
are.
But you can start the Fibonacci with any starting sequence and it still approaches.
So maybe that gets around that. So maybe there is an infinite with So the original question, and we've always, and I think we said, try to pose our questions badly, because half of doing that is getting the question posed correctly. We said, can you tile a rectangle? With broad numbers. Well, which rectangle? If the rectangle were of golden mean proportions, 1/3, then the answer seems to be.
And you have
And you have the number of tiles. Then yes, you can tile it with an option. Sequence and spiral. A lot of details were about you would if we had well enough time.
And as that man in Waterloo said, but I don't have an infinite number of tiles.
But we have a lower bound and an upper
Well,
bound.
you don't find area, just a very fine tile cutter.
Yeah, he did ask about route.
Route.
The great solution to all tiling problems.
If the original rectangle, to go back to what you said, if the original rectangle were a square, we had at chapter 3 a tentative suggestion that it could be done with a square that fitted perfectly. And that is a tiling with non-congruent squares. I think non-congruent every square is over the time.
It's a bit legalistic.
So that is the lower bound. A square can be tiled with 1, a golden mean rectangle can be tiled with an infinite number. So the next big question.
Is there anything between 1 and infinity?
Is there a finite time of other, of all, of some rectangles?
Can you draw a picture for me?
In fact, we should pass out at this point. Oh, we're going for it. Do you want to do it time?
That windmill thing someone's talking about, where you had like a central one and then 4 that kind of meet up surrounding it.
I have a transparency here. It's just somehow our close transparency they tend to disappear.
So we want a small square in the middle-ish, smallest square in the middle-ish, and 4 rings around it. Starting at yeah, that's projected.
Take one and split the pile, and they will disseminate very quickly.
Good. Yes, and another split. Another fan of the swing wheel. And the last one. So we now have 5 squares, and clearly have not covered the entire rectangle, nor does its outline make a new rectangle. Okay?
Because what I was trying to figure out is, so we're supposed to fit nicely into the corners, the 4 corners. So somehow we need to get these wings to somehow each set to add up to the same numbers. And because they're congruent, I don't think we can do that.
Wait, how is that now?
Because we can't end up with extra on the corridors, and we can't end up with extra in the corners. So they have to kind of spread out to the edges.
So you kind of dynamize this you're seeing this thing radiate from its unavoidable kind of building. And so radiate out in a symmetric way, filling the 4 corners, so that the time would have to be a little bit
I was having picture drawings of other people. It just seemed like as it expanded into the corners, you'd end up with these problems where you suddenly were getting these corridors happening.
Right. So maybe we're now back on the route of trying to can be done by saying, even with the smallest square problem avoided, no smallest square on the edge, we're still going to have a 4 corner problem. So at least one.
Putting it, thanks to the mobility of this, if we moved up to here, we definitely have a corridor problem.
But you're living structure. And what's the feeling? Are we on the route to a proof that this can't be done, or can it be done? What's it? It is are there rectangles which can be tiled in a finite number greater than 1 of non-concave squares? And you notice, by the way, if you're 10-year-olds, how technical the language has become, how sophisticated the problem has become. A 10-year-old walking into the room for the third week is doing this with what I do. But you're all very comfortable with it, and they would be, because they generated the language themselves.
To suppose we want to find such a tiling, and then the logical question would be to find the minimum number of squares we need. And if you're looking for the minimum number of squares, then the idea to cut one side with a square is not profitable because there is a rectangle left. So we know for the minimal tiling, it should be the side of the largest square should be smaller than the side of the rectangle.
That the side of the largest square
should be smaller than the one smallest side of the rectangle.
Of the initial rectangle. That's nice. Any issues about the number of squares in a possible minimal tiling? We know it's got to be at least 5. I think we know it's got to be at least 5. Do we know that?
At least 5. At least
5.
Yes.
In fact, 5 just doesn't look as if it would do it. It's got to be at least 6. Do you think? Is it beginning to look as if we're onto something? This can't be done.
I don't know, have we tried to rectangleify the 5 squares?
What do you mean?
Well, like, you know, we didn't line them up very well on the outside, so just erase the outside edge and make them match up better.
That's not one of the things.
Oh, yeah. You know, the top. There you go.
That's
better already.
Okay,
So what you notice that what I want to do is none of you have asked, but then you're all mathematicians, none of the kids ever ask, what's the point of this? Why are we doing this? Because one gets hooked. One gets hooked at the very least by one's curiosity and one's big-headedness. So, no problem like this is going to get me, it's going to stop me. It either can or can't be done. Well, I can decide. Yeah, what if this is one like this side of the door?
Right. Make it the, I'll make it a little bit wider and a little bit taller.
A little bit squarer?
Yeah.
Okay, you guys.
Tough crowd.
A little bit wider and a little bit taller.
A little bit wider. Now, I'm
More than twice as wide as the square already there. Like that. Slightly more than
like
twice
that.
as wide. Yeah, okay, with that.
And I'll do my best at square. This is very slim. Blackboards are nicer.
There you go. Now make the.
No, we can even out the top line with another square. The top line, we can even it out.
So you can continue the top to your right.
Oh,
No. Oh, yeah.
Yeah, make that square.
If this is this long,
This is going to have to be a little longer or shorter.
Well, it's gonna have to be longer.
Yeah, because theoretically, that line is more than twice the length of the square, and the line you're drawing now is a little less than twice as long.
Yep.
So, because it's matching the part left over to subtract the square.
Okay, so I will just push this down here, allowing me to draw the square on this base?
No, you have the top of the square, the line you just extended is the top of the square, now drop the line down.
Oh, so we draw this line down?
Yeah,
Oh,
that's right.
fine.
So now we've got two of them.
Yep,
Now push that up to the
now
top.
I'll push it back up.
Oh, why not push it?
There you go. And the rest is trimmed.
This is looking pretty thin, isn't it? I mean, some problems seem to have been screwed.
We have tiled an eighth of a square.
We can always adjust the size of the initial rectangle. We need a third wing.
Should I put a third wing in here?
Yeah, third blade of this fan. And now we see that there's a problem. Because if you push that up to the top, as you now have, we've got a curve.
Well, here you go, just take the top left square and make it longer. You know, the other squares look like rectangles anyway. So just take your top left, just take your top left line there.
I have a left-right reversal.
Top square, your upper square.
This guy?
No,
The other one.
This guy?
yeah.
She
Left,
reverses
the
left.
left, yeah, that line, move it out.
Move this
There
line
you
this
go.
way. So it's not gonna look like a square.
Oh, but none of the other ones do either. No, don't make it any wider. Just move that line that's already there, straight up. Yeah, there you go. Straight up from there and over.
And get rid of the line you had. Get rid of this line.
Sure.
Is that what you want, Amanda?
Yeah, that sounds good. And then we can do the same thing on the bottom right.
So what are we going to do about the fact that this is not a very good square?
None of them are.
I've not drawn anything like that and claimed it was a square.
But you know, this is a strategy.
No, don't make it go down. Just go straight over.
That's a square.
No, just go straight over. That's much too square.
By the way, you do have your own pieces of paper to try this on.
What you're about to do is going to make 4 congruent squares around 1.
No.
By the way, what happens now to step back from the problem and talk about a masterful class. The kids have gone through this for now, 3 hours to reach this point. 3 hours of 3 weeks. They've gone home in between. They've thought about this. They've talked to their friends about it. Their parents have told them, "Why are you doing this? Is this going to help you get a better grade in school?" And they come back and they say, "Look, there are certain kinds of people who can do this, and I'm not one." Which is, of course, not true. Because anyone can do this once one gets engrossed in it and have a high enough threshold of efficiency.
Can anyone prove to me that the 4 squares around it will be congruent? If we just finished it off?
You accept things by authority?
No.
You're probably not.
Well, yeah, because you're always losing a little bit of a side length when you subtract out your middle square. So they actually, if you're trying to do this algorithmic thing going around, you're always going to get a little bit, the side length is always going to be a little smaller. And so then you're going to, at the final point, you're going to have a corner missing.
You won't make it this way. But, sorry, explain that.
I mean, she's trying to make this pinwheel of squares and have it come out to be a big square, right? And it's not.
Or rectangle.
Rectangle.
Well, it won't do that either, because when it comes around, it'll be smaller. The last square will be too small to do that, and there will be a little gap at the end.
What if we name those squares? That little one, let's call that S.
Good. This is a great tactic, by the way.
Can I ask that?
Which kids do or do not come up with.
Yeah.
Naming them allows you to move up a level of abstraction. You're going to be able to use the names somehow.
And my meta question is, what do you do about when the kids come back and say some kids can do this and I'm not one?
I tend to say, this I can't do this. I have no idea if this is going to work. We're all working on it together. If you all fail together or succeed together, I don't know. That's what's so wonderful and nice. The next problem that comes up in math, it might be easy. Except for the kids. And the kids, you're not handing out the math to them, they're giving the math to one.
This approach may very well yield an answer one way or another, but this is not the way that I look at this problem. If we trace, so we've already established that none of the squares can be as long as the shorter side of the rectangle. So no square can reach from one side of the rectangle to the opposite side. So if we go around the rectangle and mark out the points that divide one square from the next, because squares have to fit along the side of the rectangle all the way across, that yields a different way to think about it that I can't really reconcile what we're doing here, but might be,
It's very nice, it's kind of the inverse process of what we're doing. We're building up, you're saying, laying out what the constraints are going to be, and let that build in.
Yeah, and I don't know that it would necessarily be a constructive approach if the question is answered in the affirmative, but it might be a way to yield a negative proof.
Very nice, very nice. Comments on that? Only because of our time constraints, we've only got amazing, just 16 minutes left. I'd like to pick up all of the mandates. This we wouldn't do with our 10-hour classes unless we were real despair. And you have to judge the students. You have to judge when that breaking point comes. When they're going to say, I don't care whether it works or not, I can't stand this. You want to cut in before that happens.
What happens in our classes is at that point we do function machines.
You suggested something about rectangles. And you suggested letter. Can we tile a rectangle with non-congruent rectangles?
Now, see, you think it's a trick question, don't you?
Yes.
Of course you can. But so what? Does that help? It doesn't help in the least. Well, it doesn't help very much. Well,
it helps picture two.
Yes. Let's tile a rectangle with lettered, non-congruent, or maybe some congruent rectangle.
There is a way to do this.
Excellent.
I still think a blackboard is necessary.
Come up a little bit. So look, we have just filled tile of rectangles with non-congruent rectangles. We have the smallest G in the middle. We have it surrounded by 4 bigger rings, sort of a pinwheel. By the way, the same is true of H. Interesting. And for what it's worth, there are 9 of them. So it's greater than the 6th that we thought might be a linear number. Yep. So the question is,
Do we hold down our flag at this point and say, well, a rectangle is a square is a kind of a rectangle, so maybe a rectangle is a kind of square, and we're done.
I mean, it seems like such a cop-out. It seems like such a treat to the kids in here. But we don't want to tile with rectangles. We want to tile with squares. I see. Oh, that was your hands for What do you think of this? Yes.
Label all the sides and set up the crazies to make them all squares.
Label all sides. Set up the crazies to make them squares. What am I? Sylvester. So look, take rectangle E and label its size, call them all X. Now, it's not visually a square, but conceptually
It
it's a square.
has been appointed a square.
And take H and label its size Y. And, I think we need the next picture. We're now racing ahead. If you call the E square, I think it was E, X by X, and the H square Y by Y, you're forced to have the square to the right, the rectangle to the right, be X plus Y by X plus Y. You're forced to have the one on top of X be now 2X plus Y. And you're forced to have the one below Y be X plus 2Y, which forces this rectangle to be X plus 3Y. Now it gets a little harder, but it's not impossible. We've only got 3 more to deal with. Can we get this to be 4Y?
Yes.
How?
If you add B, E, and G and compare that to the sum of 3, you add 5.
Terrific. So that turns out to be 4y.
Well, then, yeah.
You notice, by the way.
There's another step there, but yeah.
Okay. You notice the initial picture, with this being the smallest, is now no longer accurate. This is bigger than this square, but that's okay. You're now going to be able to get the dimensions for those two. And now, if as you suggested, you take the length of the top of the rectangle and compare it to the bottom of the rectangle, what do you get? You get 3x plus 12y equals 3x plus 12y. Wonderful. True. All that work. And we've gotten nothing out of it.
Oh,
size. Left-hand side is 2x plus 18y has to equal 4x plus 4y. We can now solve for x and y. We can equate the two sides. Interesting, toss them on to what you like to do. You get as an equation.
Throw it into your simultaneous linear equation.
What was it? 2x plus 18y equals 4x plus 4y. Simplify.
That x equals 1. So.
That x equals 1, and you get the tiling. Whoops, wrong one. It's here. This is just to make the suspense all the greater. Get to this. Here we are. Working. You get. It's going to work. You get a tiling of a rectangle with 9 non-congruent squares. The numbers inside each are there. Are there lengths?
Yeah. Yep. And we've now redrawn it to fit its physical.
So what's seen, yes.
Now, the 9 rectangles, you gave that to us.
I forced that card. How right you are.
Yeah. If you had the 10 weeks, do you always end up forcing that card?
It needn't be forced, but to get the fact that 9 is the minimal number is another 10 pounds.
Yeah.
There's a beautiful proof that a Canadian mathematician named Tony came up with. He looks at this diagram as an electrical circuit, and he talks about voltages for vertical lengths and conductance for horizontal, and as a result proves, among other things, that you can't have a time with fewer than 9 squares. But that's another thing.
So I'm assuming that these exist for more than 9, and certainly this kind of drawing could be created for more than 9. So do you chase that through with the, or do you ever get to that point? I mean, do they draw ones like this with 15, and then you work through the algebra there?
With the class that I just had this last semester, 12 to 15 year olds, they came up with this, but that was in a very nice class.
Yeah.
To ask for more, and there's so much more, we're on the verge, we're on the frontier now. There are a lot of open problems here. There's a nice theory that if the sides of the initial rectangle are commensurable, then it can be tiled with any number of non-congruent squares, any number 9 or greater. That for a 9 tile, there are 2 different 9 tiles. There are 11 different 10 tiles. There are only 2 different 11 tiles. No one understands at this point why that number differs for the different orders. So we're on the verge of a whole new world here, another new world, but on 3 dimensions. Fantastic question. We turned out to be. What about on a different surface? What about, for example, what do you make? Just what do you make of this? Yes. What do you make of this? Yes, say it, what? It's a torus. This is a two-tiling of a torus.
If I can work my way through the dimensions, where we get
And then
this here. Does it work?
well,
Sort of.
basically,
You would believe it, would
it's a two-tiling of a torus, but it's also something else. What did you say?
Yeah.
What?
I heard that.
It's a proof of the Pythagorean theorem. Yes. Because the big square, the two-tiling torus is a proof of the Pythagorean. Because the squares on two smaller sides fit into the square of the hypotenuse, which is the big square.
After it turns into a torus.
It's not known, still an open question, whether there are tilings of the projective plane, of the climb. No, I think there's a 5-tiling worlds over here. But if we stick with this torus, you'll notice that there's one problem. Actually, what you just did with your hands suggested what that problem is. And the problem that Ellen had in doing it, let's say you identify the top and bottom. Now you've got a cylinder. You just want to take the cylinder and bring the left-hand edge around to the right.
Side shrink.
What?
Side shrink.
Yeah.
Yeah. Can you do it? Can you take this cylinder, once it's a cylinder, and make it into a torus? Sorry, say it again?
I have not three dimensions.
Right. There's not enough room. So think of this as a two-dimensional torus, an infinite torus. The Euclidean plane with the top and bottom edges identified left and right. Edges identified.
And you send another cloud somewhere. Our time is up.
I'll leave you with these problems. Can you tile a 30, 60, 90 right triangle with a finite number of 30, 60, 90 non-congruent right triangles? Can you tile a 45, 45, 90 right triangle with a finite number of 45, 45, 90 non-congruent what about the equilateral triangle? This is just the beginning of a huge topic, because anything leads to everything on the frontier is everything. What an audience! Fantastic!